In this model, we are going to discuss about radiations. It is a one form of transfer of heat without having any intervening media. Okay, so that therefore the radiation is possible only for gas molecular radiations. If suppose the sun rays will be passed through our earth by the radiation process. Okay, so without doing any intervening media, that is called radiation is possible. But let us discuss in detail in this session. We are going to discuss about the introductions of about black body radiation and based on Planck's law of radiations, and finally what are the results of Planck's law of radiations. Finally, summary of the today's talk. Okay, so radiation is nothing but one of the heat transfer process. But the heat is transferred from one place to another directly without needing the intervening media. Example is heat from the sun reaches the earth. Is a very good example for a radiation process. So what is called the black body radiations? The perfectly black body, you know that perfectly black body is one in which absorb all wavelength of radiation, whatever the wavelength or incident on it. When such body is heated, it emits radiation of all possible wavelength. Okay, so here the black body is a perfect absorber and a perfect emitter. Perfect absorber as well as perfect emitter also. It is found that inside the black body, the nature of radiations becomes independent of shape, size, and the material, whatever they consist, and depends only on the temperature of the body. Okay, the radiation is called the black body radiations. So, what would be the size, shape, and the material consist of that? The carbon material coated, as well as other type of carbon-based material, as well as graphene-based materials, whatever it is. So, if the material, whatever be the material consist of this, doesn't depends on the radiation, but only the temperature. What will be the temperature of the body, that only purely depends on the temperature of the body of the radiations. Okay. Here that the energy distributions in black body spectrum is doing that one experiment based on the black body spectrum. We have to consider one black body with a different temperature is to be taken as when in the hole, very small hole is to be presented. That is called the porous material. The porous material is to be taken into our account. If you have to heat that material with a different temperature, the heat radiation is to be emitted, and that heat radiation is reflected by the concave mirror M1. All the reflections is to come into the flues per prism. The prism is nothing but according to the wavelength, to each one of radiation is to be distributed, whatever be the wavelength, whatever be the spectrum consist of. And that emitting of that particular spectrum is reflected to the another concave mirror M2, and the total intensity with respect to the particular temperature it should be recorded by the bolometer. Okay, so in that in the particular graph shows that you can recording with the different temperature. The first one graph shows that 1150, 1250, 1350, 1450, 1550. With that of temperature is going to be slightly increases. So it of all wavelength it should be recorded with that of reading of the bolometer. So the first one is going to be that if you have to increasing that wavelength, it automatically the temperature is also the constant temperature. The energy of the particular spectrum, the density of the energy density of the particular spectrum is going to increases at a maximum value, and further increases the wavelength, it automatically reducing that energy and come to that lower area. So if you are increasing the temperature and 1150, 250, so it automatically lambda m, the peak value is going to be shifted into the shorter wavelength side. This is actually shorter wavelength, and the higher wavelength sides is called the longer wavelength side. It automatically lambda m shifted into the shorter wavelength sides. Okay, so another results is going to be obtained. It automatically the total energy is going to be increases with the rise of temperature. If you rise the temperature, the energy of that particular peak value is also increase. Okay, so these are some of the informations we are getting that. For the lambda m t is equal to constant, that is called the Wien's law. From that we can calculate the temperature of the suns also. So we can record in the sun spectrums the lambda m peak is to be identified, and that V is equal to 2.898 10 power minus 3 meter Kelvin. It automatically that the constants value is to be putting on that. We got to find out the particular the temperature of the sun is also found out sorry, also found out by using this Wien's law. If suppose in that shorter wavelength sides is be obeying that Wien's law, and the longer wavelength sides will be obeying the Rayleigh-Jeans law. Okay, so if you're getting that the area of that particular curve covered by the area is equivalent to what will be the temperature, the energy density, energy distributions of that particular wavelength. So that's also equivalent to the Stephan's law. E is equal to sigma t power 4. So the Stephan's law and the energy covered by the particular curve is also equal. It's also obeying the Stephan's law also. So these are the results that will be discussed by this same graph. So and I come to that final conclusion. Final things is called Planck's law of radiation. So from that curve, we can the energy density of radiation is enclosure at a particular temperature with the wavelength of lambda plus d lambda is equal to E lambda d lambda is equal to 8 pi hc lambda per minus 5 d lambda by e power hc by lambda kt minus 1. Here h is a Planck's constant which is equal to 6.624 10 to the power of minus 34. C is the speed of light 3 to 10 to the power of 8 meter per second. And K is a Boltzmann constant, K is the temperature of the enclosure. Okay. So from that total curve covered by the Planck's idea, what will be the total wavelength, what will be the total energy density is equally distributed from the wavelength lambda to d lambda. Lambda plus d lambda is calculated as that particular energy density of that particular spectrum. So Planck proposes a quantum theory. From that, Planck proposes a quantum theory of radiations. According to the quantum theory, energy of emitter in the form of quanta is called the photons. So energy is to be distributed evenly. The amount of forming in the photons is going to be emitted. The like a sun rays is acted as a quanta of energy as like a photons. The energy of single photon is calculated as at a particular frequency nu is equal to h nu. Okay, Planck's law agree with the experiment in the entire range of wavelength. In the entire range of wavelength, we can start it from the lambda to shorter wavelength to longer wavelength sides. The entire wavelength of all wavelength sides, the Planck's law experiment is going to agree. The Planck's law reduces to the Wien's law for a small wavelength. The Planck's law reduces to Rayleigh-Jeans law for longer wavelength sides. And finally, summary of this today idea, we can have the radiation process. The radiation is nothing but one of the transfer of heat from transfer of heat without aiding any intervening media. So, example is sunlight. The sun ray passes through the earth is called the good example for radiations. So based on that particular radiations, we can come out to the black body radiations. Black body is nothing but what will be the wavelength they should absorb. At the same wavelength of light is to be emitted. The black body is doesn't depends on shape, size, material. What will be the material consist of? Only it depends on the temperature of that particular body of the system. So it automatically the law it will be Planck's verifications law. We can discuss about what will be the wavelength should consist of with respect to the temperature, as well as we have to test the temperature as well as total energy density. The total energy density is also increased when you have to rise the temperature. If you want to pick that one particular temperature is maintained as a constant, it have the very lower wavelength to go to the peak level. When you are increasing that wavelength, it will go to come down. The lambda m is each one of wavelength is going to be shifted when you rise the temperature in a shorter wavelength size. And finally, automatically, the total area covered by the particular wavelength at the temperature is equivalent to the Stefan's law. Okay, so the entire wavelength is the spectral lines is to obeying the Planck's idea. For shorter wavelength sites obeying the Wien's law, and the longer wavelength sites obeys the Rayleigh's law. This is called a total black body distributions. What will be the wavelength? What will be the wavelength versus the intensity distributions with respect to the particular temperature is to be exactly obeying the Planck's idea. According to the Planck's idea, each one of radiation is acted as a quanta of energy that like a photons. Each one of photons have the energy is equal to h nu. Okay. So with this I conclude my today idea. So thank you very much.